Hello, class. So in the previous video, we were talking about how to find a particular solution for a second order linear, not necessarily with constant coefficients, differential equation. We saw that those have a general form, right? The general form looks like this. So after you divide by whatever's multiplying the y double prime, then this is the form you're working with. So g of x is always what you get after you've divided by whatever is multiplying the second derivative. So we went through the process. The process was assuming that a particular solution had this form, u1x, u1 of x times y1 plus u2 of x times y2, right, where y1 and y2 came from the complementary solution. Then we went through all the process of how we could find u1 and u2 that actually satisfy this, meaning that we can plug them in and we get a particular solution. And we got a formula. The formula was given in terms of u1 prime and u2 prime, right? And the Wronskian of y1 and y2. And then as we saw, we also mentioned that the previous theorem in section 3.5 about what the general solution is in the non-homogeneous case, it works the same even though the coefficients are not constants. Right? Even because really what's driving that is the linearity, meaning that it's a linear ODE, not really what the degrees are or what the coefficients are. So the process is the same. If you have a second order not necessarily homogeneous, not necessarily constant coefficients, but that is linear, then that theorem works in the sense that what you have to do, you have to find the complementary solution and then a particular solution. So that's where all this work came from and why we were trying to find a particular solution again. Now I'm going to summarize the whole process in this theorem, right? So again, given a second order linear ODE in this form, where whatever is multiplying the y double prime is just 1, right? So given that, suppose that we know the complementary solution y sub c. Either it's given to us or we know how to find it if the coefficients p of x and q of x are constants, right? We know how to do that. And suppose that this is the complementary solution on some interval in which p, q, and g are also continuous, right? So a common interval for the complementary solution and where p, q, and g are continuous. Then a particular solution is given by this form where we have these formulas for u1 prime and u2 prime. So all we have to do is integrate those, and then we find what u1 and u2 are, plug them into the original ODE, the original particular solution. Now, on what interval does this work? This works on I as above. So the common interval you found here, common interval for the complementary solution and the continuity of P, Q, and G. Right. So that's it. That's the formula. Again, you can either memorize it. You'll have to memorize it for the exam, I believe. The next exam, I'm thinking of giving a formula sheet, but I'm not sure yet. So it'll depend. Or just use it enough that you remember what it is. Right. That's the whole process. Let's go through an example. Right? So find the general solution to 4y double prime plus 336y equals cosecant 3x. And remember that an advantage of this method is that now we're not restricted for the functions here being cosines, sines, exponentials, polynomials, and any combinations of those. Now they can be more general. Okay, so let's first go ahead and find the complementary solution. Right, it's linear second order, so we can do it. So the characteristic polynomial is going to be 4r squared plus 36. We're going to set it equal to 0, and I'm also going to factor out a 4. Right, so what makes this true? Whenever r squared plus 9 equals 0, which is the same as saying that r equals plus or minus 3i, where again, this comes from the identity that I squared equals -1, or that the square root of -1 is I, right? So we've done this in other videos. That's why I just go directly to this. Now we identify what our alpha is and what our beta is. So in this case, let me use another color. Our alpha is here, but it's just 0. Right? So it's still there, it's just 0. And then the beta is whatever is multiplying the I. So in this case, 3. So alpha equals 0, beta equals 3. So we know what the complementary solution is. It's going to be C1 e to the 0 times x, which is just 1. So cosine of beta x plus C2, again, e to the 0 times x is just 1. So that goes, you don't have to worry about that one. And here we change the sign for beta x. And beta is 3, so I should have just written 3 in the previous one. And again, remember this solution works on the whole real number line, so negative infinity to infinity. Now that's the easy part, as always. So now let's go ahead and find the particular solution using the variation of parameters method. As I mentioned, before you do anything, you need to make sure that your y double prime is alone. Right? We want to use the general form where we divide by whatever's in front of y double prime. So first, let's rewrite this differential equation. Divide everything by 4. Divided by 4. And now it's in the right form. Right? So your g of x is this. Right? It's that. What else? We also need y1 and y2, and that's all we need. Right? We need g of x, y1, and y2. So y1 is just given through here, cosine 3x. And then y2 is this solution here. Okay. So let's go ahead and find u1 prime and u2 prime. And now notice that, so let me mention that our q of x, because there's p and q, right? That's why we write it like this as well. They don't come into our calculations, but they do come in finding on what intervals is this particular solution a solution, right? So we need to verify that p and q and g are continuous. So what's our p of x in this case? Well, it's whatever is multiplying by the derivative y prime, right? There's nothing there, so that means that p of x equals 0. Q of x is whatever is multiplying y, which in this case is 9, right? And g of x we have above. Notice that these are continuous everywhere, right? So basically our interval of definition is going to be everything. Okay. So let's go ahead and do the work. So by the formula we have, u1 prime is going to be negative y2, right? So sine of 3x times g of x, all divided by the Wronskian of y1 and y2. So this we can probably just solve now because we're going to use it more than once. So what's the Wronskian? Remember, the first column is y1, and then its derivative is cosine 3x. Its derivative is negative 3 sine 3x. And then the next column is y2, and times its derivative. So this is 3 cosine 3x. See what that is, right? Multiply the diagonals. So this times this becomes 9 cosine squared x. Okay. And then we subtract the product of the other diagonal. The other diagonal is negative 3 sine 3x, sorry, times sine 3x. So what is that? I think that's minus sine squared of 3x. And I realized that I forgot to put a 3x inside here. Simplify again. This is 9 times cosine squared 3x. Minus minus is plus, so plus so where did I get my 9? 9 shouldn't be 9, it should be 3, right? Yeah, sorry, I don't know where I got 9 from. Okay. And here, so there should be a 3 in front of the sign. Okay, and there we go. Now we have it right. So this is 3 sine squared x. Use the identity that cosine squared plus sine squared equals 1. So you can simplify it to just be 3. Okay, so let's go ahead and plug this in and simplify u1 prime. What do we have? So let me use a different color. So sine 3x times cosine 3x, cosecant 3x. Cosecant is 1 over sine, right? So the sine 3x and the cosecant 3x cancel out. So we're left with negative. So u1 prime equals negative 1 over 12, right? Because the numerator is 1, divide the 4 on the bottom, right? So 4 is multiplying the denominator, which is 3. So we get negative 1 over 12. Now we just integrate. Let me work downwards. Integrate, u1 equals, well, -1/12x. And again, there's a constant of integration, but we only need one such function, right? So you can just forget about the constants or think that you're setting them equal to 0. Okay, so that's the work for u1. Let's find u2. So that's this work. Now u2 prime, just using the formula, is, so now we're using y2 instead of y1. Sorry, y1 instead of y2. Yeah, I was just making sure I didn't write anything weird. Yeah, so y1 is cosine 3x. So we have cosine 3x, and here we don't use a minus, right? The minus comes from the formula for u1 prime times cosecant of 3x over 4, everything divided by the Wronskian, which we found is 3. Let's simplify. Cosecant, cosine 3x times cosecant 3x is the same as cosine 3x over sine 3x. Now that's cotangent, if I'm not mistaken. So here we get cotangent of 3x all divided by 12. Now we integrate this to find u2. So here, what's an integral for cotangent? It's one that I don't know if I have memorized. So actually, let me look it up. So it's natural log of absolute value of sine x. Yeah, so it's a messy one. I remember that you have to do a u substitution. Okay, yeah. So this becomes, so we integrate cotangent of 3x over 12 dx, and this is equal to, so we're gonna get a 1/36 times natural log of sine of x, 3x. And then again, there's a plus c, but we don't need to worry about it because we only need one such function. Okay. Now we found what u1 and u2 are, so we can plug them into the particular solution. So y sub p is going to be u1, which is -1/12x times y1, right, which is cosine 3x, and then plus u2, right, which is 1/36 natural log of absolute value of sine 3x. Okay, times y2, which was sine 3x. And that's your particular solution. Now notice that all of these functions are defined everywhere, right? So there's no problems there. As I mentioned before, P, Q, and G are continuous everywhere, right? The interval of definition for the complementary solution is everything. So this works for all real numbers. So let's write the general solution. It's a complementary one plus this one that we found. And this works on all real numbers. Now, if I did any algebra mistake, just make sure to catch it and you can let me know, but I think everything here looks good. Yeah, so I don't think there was any mistake. Yeah, so I think we're good. Okay, so that's how you do the variation of parameters. Right? So we're basically using the formula that I gave you in the previous theorem. Now, let's do one more example. So this is an example of the case in which I already give you the complementary solution. So all you have to do is find a particular one. So I don't think I'm going to do all of it. Just depends on how long it takes, but let's at least start it. Okay, so let's start on this example. Again, we're given the complementary solution, so there's no need for us to find it. So what we're given is that y sub c is c1 x to the -1/2 cosine x plus C2 x to the negative 1/2 sine x. And they're telling us that this works on the interval 0 to infinity. Now, before we do anything else, let's identify some things. Right, so this whole thing would be our y1. This whole thing will be our y2. So actually, let me write that line a little bit lower. Now, before you compute what u1 prime and u2 prime is, remember that your differential equation has to be in the right form, meaning that whatever is multiplying y double prime, you have to divide by it. So let's divide everything by x squared. So differential equation becomes y double prime plus x divided by x squared is 1 over x, y prime, plus, so x squared minus 1/4 divided by x, y, equals, x squared, sorry, equals, so x to the 3/2 x squared, which we can simplify, and I will simplify that later. But for now, like that's the first thing, right? So we identify y1 and y2. Then before you use the variation of parameters method, we need to make sure that we rewrite it in the right form, where whatever is multiplying y double prime is 1, so that we can identify what our functions are. So in this case, we have that p of x is whatever is multiplying y prime, so 1 over x. Q of x is whatever is multiplying y, which is x squared minus 1/4 over x squared. And g of x is whatever is on the right-hand side. So 3/2 minus 2, right? What's that? Negative 1/4. So x to the negative 1/4. Yeah, because 3/2 minus 4 over 2. Yeah. Now, really what's needed is p, sorry, not p, is g. The reason why I always write, and it's a good habit, the reason why I always write p and q, even though we're not using it in the calculation to find u1 prime and u2 prime, they are important because they affect the interval of definition. In this case, p of x, q of x, and g of x even, they're not continuous on the whole number line. In fact, they're only continuous either on the interval negative infinity to infinity or the interval 0 to infinity. And in fact, negative infinity to 0, sorry, negative infinity to 0 doesn't work because we're taking a fourth root in g of x. So really our only option is to use the interval that's given above, 0 to infinity. So note, these are all continuous on 0 to infinity, not including 0. Then we would be dividing by 0. And that's it, right? So now you can just find u1 prime and u2 prime using the formulas, right? So I'm not going to do the integration. I'm just going to set it up. So u1 prime is going to be negative y2, which is x to the negative 1/2 sine x, times g of x, which is x to the negative 1/4, all divided by the Wronskian of y1 and y2, which again you can also do on your own as an exercise. And u2 prime is going to be now y2, which is, y1, sorry, which is x to the negative 1/2 cosine 3x, cosine x, times g of x, all over the Wronskian of y1 and y2. Integrate those, and then you'll get u1 and u2, and then you get your particular solution from that. So again, if you're given the complementary solution, even if the differential equation doesn't have constant coefficients, it's not a problem because you're given this, which is the complementary solution. Again, if it's constant coefficients, like in the previous problem, we can just go ahead and find the complementary solution ourselves. So that's it. So the method of variation of parameters, the coming up with the method, right? So the whole discussion we had is a little bit long, but once we have that and we understand the theorem, right, it all comes back to this theorem that I wrote, this summary, then it's really easy to use. You just have to identify g of x correctly, identify y1 and y2 correctly, and use these formulas correctly. I believe that's the end of section 3.6. So in the next video, we're going to start in section 3.7, which is going to be, again, some applications. Specifically, we're going to be working on how to model things that are vibrating. So think of modeling a guitar string, think of modeling some, the common example, which is the one we're going to see, is where you have a weight on a spring, and then you want to see the position of that weight as the spring is contracting and expanding. Right, so we'll see examples like that in the next section.